So, we had talked about p-n junctions and varieties of p-n junctions for different uses, and today I will be starting a new topic which is known as transistors, to be more specific bipolar junction transistors. We call them bipolar junction transistor. BJT, bipolar junction transistor. As a p-n junction contains almost all the physics which is required for the semiconductor electronics, this BJT, this transistor, bipolar junction transistor, is kind of a basic element using which you can make complex circuits for different kinds of uses. So, first let us see what is this word transistor. So, the transistor comes from a combination of transfer and resistance. So, if you write transistor, transfer, first write transfer and then write resistance, resistor, and take trans from here and istor from here, you can make this word transistor. I do not know whether the word transistor had been coined using this, but it does tell the application what kind of circuit it provides. So, essentially what is getting transferred and what is the role of resistor? It is a transfer of current, it is transfer of current from a low resistance part of the circuit to a high resistance part of the circuit. And if you do that, the power will be increased. If you have almost the same current going in a low resistance circuit and that is similar or of the same order current going in high resistance circuit, then you gain power. So, essentially what we have here is two p-n junctions, one p-n junction, the two parts of the circuit that it is here. So, one is p-n junction in forward bias, and you know that this represents you a low resistance circuit. Okay. p-n junction in forward bias, it offers low resistance. Of course, that threshold voltage has to be crossed, and after that any small increment in voltage gives rise to large current. Remember that your curve was like this, your curve was like this. So, after this threshold, any small increment in voltage here gives rise to a very large current. So, that is the meaning of low resistance. And similarly, if this junction is in reverse bias, then it offers large resistance. In reverse bias, the current is very small, you apply voltage and the current is very small, it does not change much. So, the resistance is very high. So, in a transistor you have two p-n junctions back to back, they are prepared on the same semiconductor base. So, that you have this kind of a low resistance part and a high resistance part. This low resistance part is like input circuit where you apply some voltage and you create some current, and then the other part is the output part, high resistance part is the output part. So, this is how the basic transistor application works. So, let us first look at the structure. So, you have a base, let us say semiconductor base, wafer, and which is, let us say, n type, the whole thing is n type, and then you diffuse some p type material. So, you have a NP junction, and then again you diffuse n type, and that makes another junction, something like this, that is, this is now n type. So, you have two p-n junctions, one p-n junction is here, this is one junction, and then one junction is here, there is another junction, this middle one is p, and this side is n, this side is n. Or you can have the reverse of it, you can take this basic wafer, and then you can this may be p type to start with, let us say this is p type, and then you diffuse on this some n type, and on that you again diffuse something which is p type. So, this is also a possibility. If you do this, you have a junction here, you have a p-n junction here, this side is p, this side is n, and then you have a junction here, this side is p and this side is n. So, you have two types of possibilities. This type is known as NPN transistor, and this type is known as PNP transistor. So, NPN means you have P which is sandwiched between n type and n type, and PNP means you have n, this n which is sandwiched between p and p. So, this is how it is made, and schematically if I take this kind of a cross section, I can show it as we did for p-n junction. I can show it this way. You have a junction here and you have a junction here, and let us say this is NPN. So, this is N, this is P and this is N, and you have a depletion layer. So, the same physics will go, you have a depletion layer here, you have a depletion layer here, the same things, all this, this is you have charges, but no charge carriers in the depletion layer. Remember all these things? You have diffusion, you have drift, you have biasing. So, all those things are there. So, this is how we will represent our transistor, or if it is PNP, the same story, it will be P here, it will be N here, and it will be P here. Now, you have some nomenclature. The middle layer, the one which is sandwiched between the edge ones, that middle one is known as base. So, this one is known as base, this one is base, and on the two sides you have either emitter or collector. So, one side is called emitter and other side is called collector. Which side will be called emitter and which side will be called collector? That depends on the kind of doping. So, that emitter side is heavily doped. If it is NPN, then this is N and this is P and this is N. So, you dope heavily here pentavalent impurity if it is silicon or whatever the donor ions in very high amount. So, emitter means your emitter is characterized by high doping of the impurities, whatever impurity it is, donor impurity or acceptor impurity. So, that doping density is quite high. And why the name emitter, that will be clear once we talk of circuits and currents and all that, but since it is heavily doped, it can pass on the charge carriers in large amounts. We say that it emits those charge carriers on the other side of the junction, and that is why it is called emitter. Then base is lightly doped. Okay, highly doped and lightly doped, and collector is moderately doped. Another good description is in terms of the geometrical parameters. The base, very important, this base region is very thin, say of the order of micrometers or so. This base region is very thin as compared to the emitter and collector, and in these two also the collector will have a larger width as compared to the emitter. So, there also you can make some classification which one is emitter, which one is collector, and base is of course very thin. Then comes the symbol for this transistor. You remember symbol for PN junction. PN junction we had symbols. It was like this, P side and N side. So, for transistor also we have a symbol, and this time the symbol is, you first draw a circle, small circle, to show that okay, the transistor is inside this. Then you draw a line, a straight line which represents base. So, this line represents base actually, and then you draw two slant lines, one line going like this and one line going like this. One is representing emitter, other is representing collector. So, on the symbol, how do I distinguish which is heavily doped and which is moderately doped? We distinguish this by putting an arrow. Arrow will be put on the emitter and the collector will be just that slant line. Okay. So, on the emitter you have to put an arrow, and that is how I know which of these two lines is collector and which of these two lines is emitter. How do I put the arrow? Suppose this one is emitter, suppose this one is emitter, suppose this is an emitter, this is the emitter, and suppose this is the collector. So, I have to put an arrow on the emitter. Now, the arrow is put in such a way that it goes from, arrow should go from P side to N side. Okay. P side to N side. If you bias this PN junction, if you forward bias the PN junction, the current goes from P side to N side. Remember, if you have a PN junction, you have depletion layer and all that, P side, N side, you have to forward bias. How do you connect the battery? You connect the positive of the battery to the P side and negative of the battery to the N side. This is forward biasing. And in forward biasing, you have large diffusion currents and all that, and the current, the direction of current is like this. From the battery positive, the current goes here, the current goes here, the current goes here, the current goes here, and so on. So, in the PN junction, the current goes from P side to N side, and that is the direction of arrow that we have to put on the emitter of the transistor. So, if it is a NPN transistor, suppose this is an NPN transistor, if this is an NPN transistor, in that case this is N, this base is P and this is N. So, the arrow will be like this, P to N, that is the arrow. But if you have a PNP transistor, If you have PNP transistor, then what will happen? Then this is PNP. So, in that case you have P here, you have N here and you have P here. So, the arrow will be of this type, and of course, you have to draw a line from here. So, you have one point here, you have one point here, you have one point here, and these are in fact the metallic contacts. If you think of that silicon base where you have these two junctions and then you have the depletion layers and all those things, and if this is your NPN or PNP transistor, you must have some metallic contacts. So, you should show the contact somewhere this end, somewhere this end and somewhere on the base. So, you have 3 metal contacts to connect to the outer circuits: base, emitter and collector, all 3 need metallic contacts. So, those things are represented in the symbol by say this point here and then the 3 points which are here. So, I draw a line here also, and this point the metallic contact, this point the metallic contact, this point the metallic contact. So, these are the symbols for transistors. Okay. Now, basic circuit, and which is the most widely used circuits also in many of the applications, and especially the applications which we will be using, we will be describing in this course. For those, the basic circuit is of this type. So, let me draw a basic transistor. Let us say this is that circle that we show, and let me say that this is the base that we show, and then we have emitter, and we have this collector. So, this is the emitter, this is the collector and this is base. And let us say I am talking in terms of NPN transistor. So, how do I put the arrow? NPN. So, base is P. So, from P to N. So, this should be the direction of arrow. So, this is the symbol. Now, let me draw a circuit element here. This is, let me write this NPN here. Of course, I do not have to write it now because the arrow will tell that it is NPN transistor. So, let me connect the circuit and make the circuit like this, and this is my input side. So, let me put a resistor and then a battery here. I have to put a battery here. Okay, here I have to put a battery, and I want to make this PN junction, that emitter base junction. I want to make it forward bias. This is the input side, this is the input side. This junction here, emitter base junction. So, this emitter base junction, this I want to make forward bias. How do I connect the battery? Negative which side and positive which side. So, this base is now P, and therefore, base should be connected to the positive terminal of the battery. So, I put a longer line here and a shorter line here, and then I connect it here. So, this is the input side. Now, this emitter base junction is forward biased. On the other side, I take a line here, I put some resistor here, and this should be reversed bias. In this basic transistor circuit which is used for amplification and some other applications, this normally this junction is reversed biased normally, but sometimes it gets forward biased also, but normally. So, let me try to make it reverse bias. So, how do I put the battery here? The other end of the battery will be of course connected here. We have only these three contacts. We have contacts at this emitter, we have contact at this base here, and we have contact here at C collector, and the emitter is common in fact on the two sides, input side and output side. To make it reverse bias, what do I do? Remember, it is N, P, N. So, this is N, this is P, this is N here, and this is P here, and now I am talking of this junction here, P N junction here, and this should be reversed bias. I am not connecting battery at the base, I am connecting this battery at the emitter end here. So, if it is to be reversed bias, this collector should be at this N side. So, this should be at a higher potential as compared to the base. Collector should be at higher potential as compared to the base, and then base itself is at a higher potential as compared to the emitter. Remember this part. Your base is at higher potential as compared to the emitter, and then for reverse bias, this collector should be at higher potential as compared to this base here, and therefore, you have to put a much higher voltage this side. So, let me show it by 3 cells in this battery. Okay. So, this is the basic circuit on which several applications are made. So, this is input side and this side is output. This is our output side. Now, the resistance is, this resistance here we will call it RL, load resistance, and we will be taking our voltage output here. So, this voltage can be called output voltage, this voltage between this common terminal which you can call ground, and then this point here, this is your output. The resistance on the input side, if you wish, you can write it as RI, let us say input side this. The batteries, the voltages on the two sides which we are using for biasing, they also have very special symbols. So, this battery on the left, this battery here, this battery here, this battery, this is connected to the base. This is connected to the base. Of course, it is also connected to the emitter, but that is anyway common. So, it is connected to the base, and that B is picked up, and this voltage is known as VBB. On the other side, this battery, this is connected to the collector, and of course, one end is at that common this emitter. So, this is known as V, this voltage is known as V, C, C, C for collector, here B for base. Then you have currents. So, we will talk how the current will go, but in forward bias, you know, the positive of the battery gives the current. So, this is the current going into the base from this battery, and this is known as IB. And then you have current in this, of course, if this is going like this, the current will go like this, and here the current will be like this, and this is your emitter current IE. And then you will have a collector current in opposite direction. Why opposite direction? That we will talk now. Now, this is for NPN transistor. Now, you can draw the similar thing for PNP transistor, and the only difference will be all the arrows will get inverted. All the positive of battery will become negative of the battery, negative of the battery will become positive of the battery, and that will be the only thing. I hope you can do this, or let me repeat it, it will revise your concepts. So, let us now draw a similar diagram for PNP transistor. So, I have this transistor here, and now I have this collector here and this emitter here. Okay. So, this is the collector, this is the emitter, and this time This is Pnp and the arrow should be from P to N in emitter. So, this is the arrow and this is the base, right. And from emitter I am drawing a line which represents some connecting path, conducting path. This is the common path, and then this junction, this is remember P and P. So, this is P and this is N and this is P. So, emitter base, this is the input side. So, first let us talk of input side. Here you have the junction between emitter and the base, this PN junction here, this PN junction should be forward biased. So, that N side should be connected to the negative of the battery. So, this should be connected to the negative of the battery and this P side should be connected to the positive of the battery. So, it will go like this. Okay. And then collector, this collector base junction, this junction on output side. For output side, you have to see this this junction here, this NP junction here, and this should be reversed bias. So, that P side should get connected to negative of the battery. So, you have put a resistance and then negative of the battery like this. So, this is how the connections will be made. And the symbols remain the same. In forward bias, the battery positive gives current. So, the current will go like this and here the current will go like this. This will be IB, the current will be IB here, and then here the current will be going into this. This is IE, and of course, the collector current we will talk why this is opposite. This will be IC, and the same symbol. This is VCC, this is VBB, and so on. So, this is the kind of basic circuit it has. Now, in this the emitter is common between the two sides, input side and output side, emitter is common, and therefore, this kind of connection is also called common emitter mode. Another useful configuration is where the base is made common. If you make base common, how will this basic circuit look like? Let us do that. So, once again start with a transistor and base is common. So, let me now draw the base like this, and you have emitter input. Generally we keep on left. So, this is the input, this is the emitter side and this is the collector side, and let me do it for NPN. So, the arrow should go from P to N, and hence the arrow should go this way, NPN. So, this base is now P and this emitter is N, collector is also N. So, emitter will have this arrow going from P side to N side, and then our circuit. Now, how do I put my battery, which side positive, which side negative? Once again, this input side should be forward biased. This junction, PN junction between the emitter and the base here, this is the input side. So, this should be forward biased, and this is N, this is N, this part is N, NPN. So, this should be negative and this should be positive. So, this is how the battery should be connected to make it forward biased. On the other side, the collector side, this should be reversed biased in normal operations. So, I am drawing this circuit for most of the applications which use this kind of situation. So, now you have to have this junction here between this collector and this base. This junction should be reversed bias. Remember, it is NPN. So, this side is N and this side is P, and this should be reversed bias. So, N side should be connected to the positive of the battery. So, your battery will be like positive here and negative here. This is VCC because it is connected to the collector, and this is connected to the emitter. So, this will be called VEE, right. If you compare with the previous case, we had VCC and VBB, and now we are having VCC and VEE because this is connected to the emitter and this is connected to the collector, and this is common, base is common, and therefore, base does not appear here, B does not appear here, B does not appear here. Another thing you can note that the battery polarity, if you look here and here, they look opposite to each other. You have negative drawn upwards and this positive drawn downwards. Here you have positive drawn upward and negative drawn downward. So, they look opposite polarity, whereas if you go for that common emitter mode, this battery and this battery, if you see, you have positive on the upper side, here also you have positive on the upper side. So, these are some visual things that you can talk. This will be called common base mode. So, I will be working with common emitter mode more, and therefore, we will concentrate on that. Okay, so, now let us think of let us talk of how the current goes, how the charge carrier goes, the working or flow of charges, right, working of a transistor, flow of charge carriers, and so on. So, let us start with that common emitter configuration, common emitter mode basic circuit, and so that circuit is there, and let me draw it in slightly different fashion. The same circuit, this circuit I am going to draw NPN transistor and in common emitter mode, but then I will be doing it in slightly different manner. Let me say this is our transistor, and here are the two junctions. Here are the two junctions. And this is NPN. So, this is N and this is P and this is N, and this is the emitter, this is the emitter side and this is the collector side. Of course, middle one is base. Okay, so before that, can you answer one question? This junction that I am drawing, okay, let us say at this junction, let me magnify it, this junction part. So, I have this junction here, and I am drawing the depletion layer, all right, it is magnified. So, this whole thing is first junction, this whole thing is first junction here to here. Okay. So, this is I am drawing here. Now, can you tell me where is the junction as such? This is the width of the depletion layer. In this, where is that junction? Right? You remember in PN junction we said that if this is the junction, then this is the depletion layer and this is x1 and this is x2. So, I am looking for this junction here. I am showing you the depletion layer, width of the depletion layer, and tell me where is the this junction as such. And the clue is, I will not answer this question, I will only give you the clue. The clue is emitter is heavily doped. And the base is lightly doped. So, you work out in this depletion layer at what point should be this junction. It should be here, or it should be here, or it should be here, where in this. So, do it. Okay. So, let us connect it. First, that input side, let us connect that input side. So, input side you have this is the base, okay, and therefore, then you have a some resistance here, you have some resistance here, and then you have a battery, and I have to connect positive here and negative here, and then it goes to this one. So, that this junction is forward biased, and remember this emitter is heavily doped and it is forward biased. So, what will happen? The majority carriers will diffuse in large numbers, and here the majority carriers are all electrons, right. The number of holes is small. You remember that Ni times Nh times Ne is Ni square. So, this is fixed, and if it is heavily doped N side, Ne is very large and then Nh will be very small. So, you have a small number of holes somewhere here and a large number of electrons, and then you are doing this forward biasing. So, lot of electrons will diffuse across this layer and will go from this N side to this P side. They will cross this junction and go from emitter to base. So, remember this is our base. So, from emitter it is going to base, and of course, the holes will also diffuse from base side to. So, here this is P type. So, you have some holes here, okay. You have some holes here, these are the majority carriers, but even then it is a lightly doped material, and therefore, the current is mostly because of this electrons. You remember that I in a PN junction, I is coming from holes and also from electrons. So, in this particular case that we are discussing, heavily doped emitter and lightly doped base, most of the current is coming because of the electrons only, because of the majority carriers only. So, electrons are going this way. What direction is the current? The current will be opposite. So, the current will be like this. So, current is like this. So, here the current is like this, here the current is like this. So, this is the kind of circuit if there is no other junction. But remember, so now you can justify why the name emitter. Why the name emitter? This emitter has emitted or it has injected lot of majority carriers on the other side, lot of electrons on in the base side in this NPN transistor circuit. If it is PNP, then lots of holes will be injected, lot of hole will be emitted. So, that is why the name emitter. Now, you can justify why it is that. But the base is very, very thin, and again you have this second PN junction here, which is reversed bias, all right, which is reversed bias. So, let me draw this side of circuit also. You have this this resistance here, and then you have another battery here, and then it is connected. So, you have a reverse biasing on this other junction. This junction is reversed bias. And what will happen? You have a PN junction, this junction, you have a PN junction. So, let me magnify this again. Suppose this is that junction, second junction now I am talking of. This is that other junction here. This side is P and this side is N, and it is reversed biased. So, this is positive and this is negative. Let us say this is negative. So, this is reversed bias, and you have lot of electrons here. So, what will happen? What will be the direction of current as such, or electric field? Let us first say what is the direction of electric field. If you have a reverse bias and you have connected the positive of battery here, then the electric field will be in this direction, in the junction. The electric field is in this direction, and that electric field will draw the electrons towards the collector. Look at the figure. You have lot of electrons which have crossed here. From the emitter, lot of electrons have come, right. Your emitter is somewhere here, the other junction, the other junction here. So, from this side lot of electrons have come. So, these electrons have come here, and then this is very thin. So, it immediately sees that depletion layer. So, these electrons go to depletion layer. In the depletion layer you have electric field. So, that electric field will immediately draw them to this collector side. So, those electrons are now coming this way, the electrons are coming this way, and therefore, you have a current here. This is the current IC. Okay. So, the current is from collector to base, opposite to the electron flow, and therefore, the current in this collector is in this direction. The current is in this direction, and this current must come from the battery, and therefore, this IC is in this direction. So, this is IB, this is IE, and this is IC. So, that is how the currents are drawn. Now, of the large number of electrons which are emitted or injected into the base region, lot of them are being drawn in the collector because of this reverse bias, but some of these electrons are able to recombine with the holes here. And in a circuit, finally, all charge densities, current density, currents, and everything should be constant. You cannot have accumulation of charges in a circuit, right. In a steady circuit, you do not have accumulation of charges, and therefore, if you have a recombination here, if electron is getting lost here, that has to be compensated, and that is done by this battery. So, if there is a recombination somewhere, you have another whole electron pair which is generated, and that electron flows into this battery and makes up this current IB. Okay, so it is a clumsy figure, but you can apply the Kirchhoff law at this point. Let us apply the Kirchhoff law at this point. What you see? You have a current IB. See this current IB. This current IB must go here, because there is nothing in between. This is a series connection. So, this IB should go like this. Similarly, this IC which is coming, collector current, that must come like this, and that must come like this. So, this is IC, and here it is IE. So, you can immediately see that this emitter current is equal to the collector current and plus the base current. Any guess about the relation between this IC IB, which is larger, which is smaller? Once again, since a lot of electrons are being injected from the emitter to the base, and most of them are getting drawn here, only a small amount of electrons contribute to this base circuit. Therefore, IC is going to be very large as compared to IB, or you can say IC is close to, it is smaller than of course, but close to this IE. Most of the emitter current is going through the collector. So, this collector current is IC is almost equal, slightly smaller than this. Typically, this IC is let us say some 95% to 98% of IE. The remaining 2% to 5% that is going through the base, and we define a parameter which is called beta, which is IC over IB. This is known as beta, and this parameter will have, typically it will have values from, let us say, 20 to 50 or like that, depends on the construction of a transistor. And in the applications, we are actually not looking at the DC voltages and DC currents, because those are for proper biasing of the circuit. We are actually looking at the incremental changes. If I increase this base current by little bit, what will happen to the collector current? And therefore, this beta, you can write this as beta DC. This is the entire current IC and entire current IB. But you can also define beta AC, which is incremental change in this current and incremental change in this. Not much difference, in fact, beta AC and beta DC are roughly the same, and so one only talks of beta. So, this is how it works in this circuit, the kind of circuit that I have talked about. The emitter is once again, let me draw a fresh diagram. So, the emitter, just a revision I am doing. So, this is, let us say, NPN. You can redo entire thing with Pnp, only the roles of electrons and holes will be interchanged, the directions will be inverted, and other things will the discussion will remain the same. You can talk in terms of majority carriers and minority carriers, then it does not matter whether it is NPN or PNP. Okay. So, what we did, we did the circuit. If I draw that symbol, it is here, this is N, P, N. So, the arrow will be like this, and then we have this circuit here, we have this circuit here, this is N and then P. So, it is like this. You do not have to remember when to put positive here, when to put negative here, you only have to remember that the input side is forward biased in a normal circuit. So, it is like this, and similarly here you have this other part, output part, where you have so we are talking of this circuit. Okay. We are talking of this circuit here, and the working is that when you forward bias this, then you have lot of current, lot of charge carrier injection of majority carriers. So, this injects lot of electrons across this depletion layer here, across this junction here, and then most of them are collected. Most of them are collected by, let us say, this collector. So, of these electrons, lot of these things are collected here, and therefore, you have a current, corresponding current. Then you also have a little bit of current through that base also. So, this is I am showing the electrons flow. Remember, the current will be opposite to this, and this is because of the reverse biasing here, So, that is how this thing, the electrons will go through this circuit like this, will go through this circuit like this, and so on, and then here they will be injected back into this. Remember, in a circuit, the number of charge carriers, all the voltages, currents, everything is stable. So, if the electrons are going here, the electrons must be compensated, and that is coming from these two batteries. Making up the total current of IE. So, this is how the transistor circuit works. Now, in PN junction, you had some characteristics, right? Remember, in PN junctions, we talked of IV characteristics, and we say that if I have a PN junction here, I put it in some circuit, and the voltage across the junction is say V and the current going through this junction is I, then IV characteristic we plotted and we had some figure like this, some threshold, and after the threshold it increased rapidly. So, the current was very small and after some threshold it increased quite rapidly. And on the other side, on the reverse side, you had a very small current and we said that okay, you change the scale so that it is at least visible. So, this is IV characteristics. So, whenever you have you apply a voltages and a current results, you always ask what is the relation between that I and V. If it is just a resistance, that IV characteristic of a resistance is very simple, it is just a line, straight line, ohmic resistance. If IV is for resistance, it is very simple, it is just ohmic like this, straight line like this. So, there you have a fixed resistance, but for semiconductors is non-linear and all that. Here I have two different parts of input side and output side. So, in the transistor circuit I can talk of various characteristics. In a transistor circuit I can talk of various characteristics. Once again I am drawing this this figure. This is which transistor is this, NPN or PNP? From the arrow you should now you should be able to tell, answer these type of questions. So, this is that input side and the output side is like this. This is RL, this is RI, this is VBB and this is VCC. Remember, this emitter is common. So, if I talk of the input side and talk of the voltage which is there in between this base and emitter, that is my, let us say, input voltage VI, VBE, base and emitter, this voltage between this base and this thing VBE. Of course, that VBE is slightly different from this VBB because of this resistance here. If there is a current IB, then you know VBB minus RI times IB will be this VBE. So, this you can take as the input voltage. And IB you can take as the current, input current. So, if you draw a graph between this IB and this VI, that will give you characteristics of the input side. So, that is known as input characteristics, input characteristic. Which is IB and VBE. This graph is known as input characteristics. Similarly, on the other side you have output, and here you can take this as the output, this is the output, this is VO. So, you can take this as VO, output voltage, and then the current is IC here. So, on the output side, if you plot this relation between the output current and this output voltage, you get this output characteristics. So, that is between IC and VO. So, you will get output characteristics. You can also have a relation between one parameter from input side, one parameter from output side, for example, VO and VI. So, if you take VO output voltage and then you have this input voltage. So, you are taking one parameter from input side, one parameter from output side, that you call transfer characteristics. Okay. So, we will stop here, and next lecture we will talking of all these input characteristic, output characteristic, transfer characteristics and so on.